Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Jordan Steckloff with us and Jason Soderblom with us. Hi, Jordan. Hi, Jason.
Hi.
Let's start with Jordan. Jordan, what's your geolocation?
Geolocation. I am in Southeast Michigan, just north of Ann Arbor.
Ah, okay.
Yeah.
How about you, Jason?
I'm in the Boston area.
All right.
West Roxbury neighborhood.
Triangulating here. Those are some pretty interesting rocks behind you there, Jordan. Anything from Titan or other solar system bodies?
Yeah, actually, about, let's see, almost 2 years ago, January 2018, there was actually a meteorite fall about 10 kilometers away, 6 miles north of here.
Cool.
And so this is Michigan. There's lakes everywhere, and this is January in Michigan, so the lakes are frozen and they're covered in snow. And suddenly the Hamburg meteorite scattered meteorites all over these frozen lakes. So all you had to do was walk out onto the ice and look for the black thing on top of the white snow.
Yep. Very cool.
It is the only meteorite search I've ever done, and I can't imagine it'll ever be easier than that. So I have a couple specs from that and a few impact shatter cones, and then some random shape models of small bodies.
So was that an iron meteorite, or was it carbonaceous, or?
It was I believe it was finally categorized as an H5. So it's not an iron meteorite. It's a pretty standard stony meteorite that it's in I think they call it an ordinary chondrite. It's pretty ordinary. But I think it's pretty great. It fell nearby, and what was great is because it fell in a populated area, and it fell on this ice, and people were able to scour it right away. We're able to recover these meteorites very quickly, and with all of the modern, video doorbells and security systems that people have all throughout the Detroit area, we were able to, I helped a team that was led by Peter Brown to try and triangulate with the trajectory of this object, and from that you can extrapolate what its orbit actually was before it intersected the Earth. Okay.
What was the total mass that came in?
So the mass of the original asteroid was just something on the order. I was told it was about the size of a refrigerator. That's what they think it was.
Okay.
Now, I don't know if it was like a side-by-side or a mini fridge, but that's roughly the size we're talking about is household appliance.
Cool. That is awesome. Jason, you got a very appropriate shirt on there for what we're probably going to hit soon.
Yes, indeed.
Is that a team shirt?
It is a team shirt. It's actually a logo that I developed with Jason Barnes and Shannon McKenzie for our project.
Very good.
It's an infrared image of Saturn highlighting methane molecules, 5-micron emission, and water absorption.
Very cool. So is that an iron-on or is it a patch?
No, it's a patch. It's through Land's End.
Awesome.
Sewn on, embroidered.
So it'll last.
Yeah.
Very cool. Very cool. So Jordan, Jason, what do you guys like to do for research? One of you go first. In general, what do you like to do for research?
Just about everything.
Everything. This guy's awesome.
well, I should clarify. Everything with the caveat that as long as it's simulation based or theoretical. I haven't really done lab work or observing, but I've worked on everything from Mercury out to Pluto and beyond, small bodies, airless bodies, Titan, exoplanets, but usually nothing large and gassy.
All right, Jason?
Yeah, similar, which is I think why Jordan and I work together so well. I've got projects right now looking at impact cratering on the moon, atmospheric radiative transfer in Martian's atmosphere.
Cool.
All kinds of stuff on Titan, surface, atmosphere, near surface, impacts into Titan, kind of all of the above. But we've got a really fun group that Jordan and I are both part of, which is looking at the hydrocarbon cycle on Titan. And so we've kind of been building up a large team with lots of different proposals and a number of funded projects right now, kind of just looking at this whole cycle of hydrocarbons on Titan and methane, the methane cycle in particular, and kind of focusing on each different aspect with different groups that we kind of get together about once a month and discuss where we are and what we're learning. So that's been a really fun collaboration.
Very nice.
Yeah, that's probably a better way of phrasing it rather than what do we work on. It's more of what type of processes do we study, and everything that I tend to work on tends to involve phase changes of some sort, whether it's sublimation from solid to gas or from gas to or from liquid to gas or back and forth. It's what I find really interesting is just how these different phase changes vary as you go about the solar system or different environments and from different materials. And then also what effects can these types of things have on the properties or behavior of objects themselves.
Awesome. And that is going to take us to this really lovely Planetary Science Journal paper. And for those who don't know, this is the AAS Journal's latest journal. It's all open access. So if you'd like to get the real deal, you can go to it and download it. It's all gold open access, and you can go. So stratification dynamics of Titan's lakes via methane evaporation. And Jordan and Jason, take us away.
Yeah, so this was a fun project to work on. It builds on the observations that Titan's got stable liquids on its surface. It's dotted with lakes large and small, some of them larger than Lake Superior, and presumably there are many lakes that we just can't resolve, but there's some evidence that they're there. Either we think there might be specular reflections, but I'm sure Jason can speak more to that. And Titan's the only other place other than Earth that has these stable liquids on its surface that we know of. And one of the questions we wanted to figure out is, well, how Earth-like is Titan, or equivalently, how Titan-like is Earth? And so one of the things we wanted to understand is what are some of the dynamics that these lakes can experience? And on Earth, we have water. Our surface liquids are water with some solutes in them. With seawater, you have salts. There are some lakes that have fair amounts of carbon dioxide dissolved. You get like soda springs, or there's lakes in volcanic craters that can dissolve a lot of these materials. And this can change some of the properties of the liquid. Typically, we think of these as increasing the density.
Mm-hmm.
And with seawater, it's not a huge change. It's a few percent relative to fresh water. Most typically, there are some extreme examples. You go to the Dead Sea, and now you're talking about Dead Sea being 20 to 30% denser than fresh water. Mm-hmm. And so there you get some of the largest property changes that we see on Earth, but generally it's just generally a few percent. And on top of that, on Earth, we also see that temperature can change these properties. In temperate lakes, especially in North America, specifically where I am, in the summertime, the tops of these lakes, they warm up with the sun, the water expands, it gets a little bit less dense. It's not big, on the order of 1% or so, if not that much. Mm-hmm. But it's enough to make it noticeably buoyant. And so this warm water, and this layer builds and it grows and it stays warm, and it doesn't mix with the water below because it's floating on top of it. And so if you've ever dived into a lake that is, that is stratified like this, that surface layer feels relatively uniformly warm. And then you can get to, if you go deep enough, you hit this point where suddenly it just gets very rapidly frigid. And this is called the thermocline, where the temperature changes very rapidly. And that's where you're transitioning from one layer to the other. And so, and then in the fall, the surface cools down and the water gets denser, and eventually gets denser than the layer below, and the whole thing mixes due to density-driven mixing.
Thermal hailing.
And so on Earth, we typically see around here mixing twice a year. Once in the fall, when the top layer becomes denser and it stirs in, and then again in the spring as that surface layer warms up, and just due to the unique properties of water being densest at 4 Celsius. And so, but these are all different processes that change this fundamental property of density of water on Earth, and all of these stratification dynamics and this mixing and unmixing of of these bodies is driven by the density. And so we wanted to look at is what types of processes on Titan can give us unique density changes that could give us similar behavior. And so we focused on what is presumably the simplest case to look at, some of these ephemeral ponds. So we've seen rainstorms move across Titan, and it looks like they're filling in these topographic lows with liquids. And so we wanted to know this simple case. We have a liquid, it's relatively shallow. So the first order, it's a uniform pressure. It probably starts out at the same temperature, well mixed, just nice ideal case. If we start with an ideal case, what could happen? Now, on Titan, we mentioned we're interested in the methane cycle. And so we have these methane rains, they come down. And over time, we evaporate methane out of these lakes back into the atmosphere where it can then rain down again. And so uniformly on Titan, when we form these lakes, we expect that they lose methane over time, which means that everything that's not methane gets more concentrated. Typically, we're talking about ethane and nitrogen, dissolved nitrogen from the atmosphere.
Okay.
And so we want to know what happens as we lose this methane and go from methane rich to methane poor. Can anything strange happen? And it turns out on Titan, there's a very strange behavior with the way that its density behaves. So on Earth, the densities are driven either typically by temperature, with thermal expansion or contraction, or just through direct dissolution of salts or other solutes. And on Titan, it's a little different. It's driven by dissolved materials, but on Titan, the liquids are typically dissolving atmospheric nitrogen. And nitrogen makes these liquids very dense.
Yeah.
So, if you add nitrogen to the liquid, it's going to get denser. If you remove the nitrogen, it gets less dense. But the amount of nitrogen that dissolves is very sensitive to both pressure and, as we talk about in this paper, temperature. So as we cool the liquid off, we dissolve more nitrogen from the atmosphere, and the liquid gets a lot denser. And so, but it's a complicated relationship, because if we have a mixture of methane and ethane, the methane wants to dissolve nitrogen from the atmosphere, while the ethane tends to prevent it. And so as we lose the methane, we go from a liquid that really wants to dissolve a lot of nitrogen and become very dense to a liquid that does not want to dissolve a lot of nitrogen and become less dense. And there's some interplay between how ethane's denser than liquid ethane's denser than liquid methane, but it's less dense than liquid nitrogen. So we get this very complicated behavior as we go from one end member to the other. And the end result of this is that we get some very strange patterns in the density behavior of liquids on Titan that can lead to stratification and overturn if the conditions are right.
So you mentioned that the rain fills in these low-lying geographic areas. Do you see these smaller lakes completely evaporate?
Jason?
Sure. Yeah. So it's actually the kind of the background or the justification for this project, and the reason we started looking into this was, as Jordan mentioned, there's a couple of rainstorms that we have seen on Titan, fairly convincing evidence where we see large sets of clouds go through, either from Cassini or from Earth observations. And when we compare before and after images of the ground, we see large regions of the ground that have become dark. And so that's pretty strong evidence that something has precipitated onto the ground. These are large enough regions that you wouldn't expect, for example, winds to just come through and blow away dust and change the albedo of the surface. Right. So surface wetting is definitely the most obvious thing. And with some follow-on work that's going to be published alongside this, we see clear evidence that the regions that become dark correlate with what appears to be topography, so topographic lows. So it looks like not only is it wetting the surface, but it's actually collecting and pooling. But what is really intriguing and fascinating is, and this was first published in a paper that Jason Barnes led, the surface after it darkens some months in the case of an equatorial storm, and years in the case of a south polar storm, becomes very bright, significantly brighter than the original surface albedo. And so that was the original problem we're trying to understand. Our best guess is that some sort of ice is forming and precipitating out of the fluid, or forming and floating on the fluid surface. We're not really sure. Other ideas have included fine-grained material being leached out of the subsurface and being left as a lag deposit. But ultimately, getting back to your original question, yes, it does appear that this liquid is somehow evaporating or infiltrating into the surface, but in some way it's leaving these reservoirs so that this bright material can be exposed. In the case of the equatorial system, the brightening reverted back to a more neutral environment, more neutral albedo after a few months. In the South Polar region, we see evidence that this brightening lasted for at least a few years, after which we no longer were able to acquire images with Cassini. So that also suggests that there's some sort of a temperature dependence, some sort of a thermal driver to this, so that's kind of consistent with this idea that it's some sort of an ice forming on the surface.
Cool. All right, we'll slide through. I think we did a good intro there. Want to talk about Titan Pool?
Sure. So real brief, Titan Pool was something we wrote using a lot of existing codes that we in models that we describe in the paper. But the point of Titan Pool was to understand what are these materials' properties on Titan. So if we say that there's a certain set of conditions on the surface of Titan, or even subsurface of Titan, what would be the properties of these liquids? What would the density be? What would the composition be? In particular, we're wondering if we tell you how much nitrogen, if we tell you how much methane and ethane is present, how much nitrogen would dissolve in equilibrium from the atmosphere, and from that we now have a composition. What would the for a given temperature, we could ask what would the density be? And so Titan Pool is a code that builds on a lot of other work, but allows us to calculate these properties quickly and efficiently.
And it's going to be fairly sensitive to the equation of state and perhaps uncertainties in the equation of state.
Right. And so so one of the issues with studying liquids on Titan is that there is a dearth of ground truth that we actually have on these liquid properties. That's not to say there's no lab work. There is some good work that has been done in the past and that is still being done. And so, but it hasn't made its way into a lot of these equations of state yet. So we're using Titan Pool uses it's called the GERG 2008 equations of state that you can find in RefProp. Which is an industry standard code that is really useful in a lot of industries, particularly oil and gas extraction, where you really want to know what the properties of methane in a nitrogen-dominated atmosphere such as Earth, how those would behave, what the viscosity would be, so you can extract these resources from the reservoirs, or you can understand the conditions for transporting them, or for refining them through various processes. So this equation of state is really, really good for trying to understand how things behave on Earth with Earth-like temperatures, Earth-like pressures, even in various industrial processes.
Right.
We're taking this code and stretching it to its absolute extremes. We're taking this equation of state and applying it to the very limits of where it can be considered reasonably accurate. That's not to say that's not accurate. It's that there's very little data to continue to refine the equation of state at around 90 Kelvin. So what we did is calculate a bunch of these properties using Titan Pool, and then we compared them with some really high quality laboratory data just to verify that how accurately it is computing these properties and what these errors might actually be. And for what we found is that for the temperatures and for the pressures that we consider, we're accurate to within a few percent, maybe 10% for some properties.
Uh-huh.
But that's more than sufficient for our purposes.
Right. Okay, cool. Let's take a look at some solubilities.
Yeah. Okay. So I look at this plot or these two plots, and I think they're really fun because when I look at this, I see some very strange wavy behavior, which to me suggests that there is some very interesting physics that or processes that might happen. All right, so let me describe what we're looking at here. We're plotting two properties. On the left, it's density of the liquid. On the right, it is the equilibrium amount of nitrogen dissolved from the atmosphere. Or in this case, it's what's the mole fraction or mole percent of nitrogen in the liquid as a function of the methane ethane content. So we're assuming ternary mixtures of methane, ethane, and nitrogen. And what we're doing on the horizontal axis is specifying what that methane ethane composition is. So what we're specifically calculating is the methane alkane fraction of the alkanes, methane and ethane. What fraction of that is methane? So 0% means no methane. 50% is equal mixture of methane and ethane. 100% is all methane, no ethane.
Okay.
So in this evolutionary process that we've described, where you rain out a bunch of liquids, or you have liquids on the surface of Titan, and then methane slowly evaporates, what's going to happen is the liquid is going to move from right to left on these plots. We're going to go from a lot of methane to less methane. And so what this means is that, for a given starting condition, we can look at how the density of this liquid evolves over time. Or equivalently, we can look at how the nitrogen content evolves over time.
Okay.
And so what we see is that for warmer liquids, toward the bottoms of these graphs, the reds, above basically 90 Kelvin and above, which are considered to be typical Titan temperatures on the surface, it's pretty monotonic behavior. As you lose methane, you become richer in ethane, and there's not a lot of nitrogen dissolved, so the nitrogen doesn't affect this parameter very much. And so as a result, you go from effectively the density of liquid methane on the right to the density of liquid ethane on the left. And there's not a whole lot of variation in there. It's a pretty uniform increase in density. So what this means is that if there was a liquid or a puddle or a pond on Titan that was at this temperature, it would start out at a low density. The surface would evaporate methane, and as the surface lost its methane, it would become denser as the surface moves left on this plot. And because it moves denser, it would sink into the bulk pond, and it would just continually mix until the entire bulk pond just slowly moves to the left on this plot. And this is what we would typically expect for a long time on Titan. But what we find, though, is that there's this break in this monotonic behavior at surface pressures when you get to about cooler than around 87 Kelvin or so. At that point, we have this local maximum, local minimum starting to form. And so what this means is that if we start with that same pond, just at a slightly cooler temperature, say 87 Kelvin or 86 Kelvin, or 86 or 85 Kelvin, it would follow a very different evolutionary path as it loses its methane. It would start out with the surface layer losing methane, and it would, and as long as the density got higher as it lost the methane, it would mix in like before. What we see here is that at these cooler temperatures, there's this local maximum, and as the pond moves left, the density, instead of continually increasing, starts to decrease. So what does this mean? This means that as the surface layer continues to lose methane, it will become less dense. And if it becomes less dense, it's not going to sink and mix with the pond below.
Right.
So what's going to happen as a result is there's going to be this buoyant lower density layer that slowly grows and floats on top of the liquid below. What this means is that we're going to stratify these ponds. So we have a less dense layer on top and a more dense layer below. But what's interesting here is why it's stratified. It's stratified because the surface and the lower layer now have different compositions.
Yes.
The surface layer is going to be methane poor and relatively ethane rich, whereas the layer below is going to be methane rich and relatively ethane poor. And so we can actually compositionally stratify these lakes as they lose methane. Now, at some point, we hit the local minimum on these plots, and then further methane loss from the surface will then continue to increase the density. And at some point, if the density of the surface layer increases enough, it'll exceed the density of the layer below, and then it'll mix in, and then this process can start again. And so it can lead to this cyclical stratification process on Titan that is analogous to the cyclical stratification we see on Earth, but it's driven by a very different process.
Very cool.
Yeah. So, yeah.
So are these calculations a sequence of equilibrium models?
Yes. Yeah. So we should be explicit. This is a series of all these calculations are assuming equilibrium between the liquid and the atmosphere, specifically for the amount for nitrogen.
Oh, good.
We do not assume that the methane in the liquid is in equilibrium with the atmosphere. Otherwise, we wouldn't be evaporating methane.
Right. That's fine. It's great. Okay. Very good. Covered that. Ooh, we got some walking back and forth here on the cyclicalness.
Yeah. So actually, this is a fun place to stop, to pause for a moment. So this figure 2 here, this tries to illustrate that process we just showed, where the stratification becomes cyclical. Yeah. So this is a relatively confusing plot if you haven't read the caption with the
long caption.
With the alphabet soup here. But what we're trying to do is walk through the steps of how the stratification works, where once you hit this local maximum, the surface layer drives down to this local minimum, the note here at the point C, at which point it's stratified and you have a maximum density difference. And then further evaporation decreases the density difference until the densities are equal, and further evaporation causes the whole system to mix. Now, it turns out if you get cold enough, around 84 Kelvin or below, you'll never overturn. And that's because even if the surface layer were to lose all of its methane and become effectively an ethane-methane mixture, it would still be less dense than the layer below, which means it can permanently stratify at these temperatures. This is called a meromictic lake. It will not turn over. And so what this means is, if we were to look at something like this, now to be clear, there's no observational evidence that these have been seen or exist, but it's theoretically possible. You would see a lot of what you would detect depends on the method with which you try to detect it. If you're looking at spectroscopy, which measures the surface layers of a system, you would see that there's almost no methane in such a lake, and it looks to be ethane and nitrogen rich.
Yeah.
But that would be omitting the methane content of the layer below if that lake were stratified. If you had a different method, say with radar loss tangents, one could determine the composition of the entire column of liquid, in which case one could detect that methane component below. And so this type of behavior has interesting implications for what one might actually measure on Titan, or at the very least for interpreting it, if the conditions are right for a stratification. And then if we could just go to the image just to the right.
Yep.
So this one's actually particularly fun. So we're trying to understand what happens when these lakes overturn. And so we have a surface layer and we have a layer below, and suddenly they have to mix. And so what we're plotting here is what the composition is on the of the layer below and the composition of the layer above. And there's this dotted line, this mixing curve, which depending on the relative sizes of these two layers, once the system mixes, you should land somewhere on this curve. Now, if we're toward the right of this curve, where it's that little purplish region labeled unsaturated, mix, nothing happens. The liquid wants to dissolve more nitrogen from the atmosphere, so nitrogen from the atmosphere goes into the liquid, and then it starts to evolve again. But this red region, this orangish region, is interesting because if the conditions are right, that we end up in this orange region, the liquid upon mixing will be supersaturated in nitrogen. What this means is more nitrogen is dissolved than wants to be dissolved in equilibrium, and so it has to go somewhere. It's like taking the top off of a pop bottle.
Yep.
It'll start to bubble and exsolve, potentially explosively, and we should see significant exsolution from the liquid. And this has been seen in laboratory studies.
Yep.
From our colleagues at University of Arkansas, Kendra Farnsworth and Vincent Chevrier and some others.
Good shout out.
So one of the predictions of this cyclical stratification behavior is the potential for producing these exsolution events, where many bubbles are produced very rapidly if the conditions are right to do it. This is certainly a region of parameter space that seems to be plausible, and could explain some things on Titan. Whether or not it explains the magic islands that we're seeing on Titan, this random these high albedo features that appeared in some images and not others on lakes. It's possible, it's plausible, but there's a lot of ideas of how those could form. This is certainly not the only way you can do it, and what's the best explanation is still an unsolved problem.
So that's a curious terminology. Why do you call them magic?
Well, the short answer is I didn't come up with that.
We have any wizards on the line who can talk about magic islands?
Well, so it's quite simple. You're observing Titan. There's this thick cloud deck you can't see through.
Sure.
And Jason, correct me if I'm wrong, but these were radar observations of some of the largest lakes on Titan. They look at the lake and it's great. They see the shoreline. They see the center of the lake. You can even measure the depth of the lake from the radar returns off the bottom, which I think is a particularly cool way of
very cool
astrobathymetry. And you do this over multiple flybys to sort of build up this understanding of what the shoreline shaped bathymetry of these lakes look like. But on some of these images, there's this feature that appears in the middle of Kraken Mare that wasn't seen before, and it wasn't seen afterwards.
Okay.
It looks like an island just appeared and then disappeared.
Huh.
And so this led to the name the Magic Islands.
Got it.
Titan.
Huh.
Now, no one thinks that there's islands forming and disappearing. So the question is, what's happening that's making it look like these things are appearing and disappearing?
Yeah.
And one of the ideas among many is that there could be a foam or bubbles being produced that's giving us this reflection that looks like land.
Okay. I'd prefer a Mauna Kea popping out of the lakes, but okay.
And then disappearing right away.
Yes. Very cool. Okay. Oh, and now we're going to do some laboratory astrophysics. Looks like some stuff done right up the road from me here at NAU. Yeah,
so there's a group at NAU, Jennifer Hanley, Will Grundy, Stephen Tegler, Anna Engel, Logan Pierce. I know I'm missing some people who are involved in this work, and I apologize. But they've been phenomenal at trying to see if we can detect this experimentally, this stratification behavior.
Okay.
They have some unique capabilities in their labs that some of our other colleagues don't have, just due to different setups in the way they do in the way laboratory experiments are done. And with their system, they were able to force the system into a stratification process that seems to match very closely with what we see. And I think we have an actual figure of that later on. That actually, here it is. That actually shows the vapor. I think it's figure 5. We have this vapor layer on top. You form this epilimnion, or this upper layer on top, hypolimnion, or the lower layer below. And you can even see this layer between them where there's this very rapid change in material properties and material density, which typically means there's a change in the refractive index of the liquid. And so we can actually see this chemocline, this rapid change in the chemical composition of these two layers. Okay. So it's always fun to say that we think this happens, and someone's like, "Yeah, we saw that in our lab."
Well, that's even better.
Yeah.
Very cool. So these are this must be Raman or something.
Yeah. So yeah, they have Raman spectroscopy spectrometers. They can analyze this.
Cool.
And I'm really amazed by what a lot of these laboratory groups can do, because it's well beyond what I would think of doing. I think it really illustrates a lot of the collaborative nature of a lot of this work, of just how the work becomes so much better when you bring more people into it with different capabilities to show different aspects of it. And we love collaborating with people, forming new partnerships, and just seeing things that we otherwise wouldn't be able to see.
Maybe you know, or help give me, what is the physical scale of this thing? Is this thing a meter wide? Is this thing a millimeter wide?
Oh, it's really small. So as the theorist, I'll tell you it's on the order of centimeters. The exact thickness, the exact thickness I can't remember.
Order
I
magnitude.
think it's about a centimeter in diameter.
Yeah, is it about, yeah, okay.
Okay, very good.
Yeah, it's a small laboratory scale, and this is their system uses a helium compressor so that they can run a refrigeration cycle down to very cold temperatures.
Mhm.
Theoretically, they can get this down to 30 Kelvin, if not lower, if they need to.
Okay.
Which is more than for Titan. We're typically wondering what's happening between 60 and 100 Kelvin, so it works great. And then this is connected to a bunch of other systems for a fixed gas volume, but it's really nice to see this in this small little cryogenic chamber form.
So let me, I got all kinds of questions. So let me loop back to what we talked about in the beginning. So I don't know if you can get this out of these experiments, but I'm wondering if you can probe either doing an experiment, so it's Gibbs free energy. So can you probe the equation of state through these, and then go ahead and loop back to the tables that are being used? I don't know if you can extract this kind of info out of this experiment.
Yeah, so the short answer is yes. The longer answer is yes, and this group's actually doing that.
Cool.
They're exploring a certain part of the equation of state of ethane, methane, nitrogen mixtures on Titan. So Jennifer Hanley is leading this study to understand just how these phase changes vary as a function of properties, pressure, temperature, and composition. Where do the liquids freeze? Where do the liquids evaporate? Which part evaporates? It's really exciting stuff, and we really can't wait for their results.
Very nice. Very nice. Okay.
Yeah. So what I think is really interesting about this work is that we're only looking at an ideal case, a uniform pressure from top to the bottom of this column of liquid. And we're looking at, here we're quantifying some of the errors in Titan pool for various experiments that were done.
Oh, very good. This is my question. How about that?
Yeah. So what we're trying to do here is if there's an experiment with a known composition, and you measure the temperature and the pressure, what is the density Oh, I think it's pressure. Yeah. What is the pressure that was measured? What is the pressure that Titan pool predicted? And then what's the error in that? We're seeing that the errors are typically pretty small. At certain temperatures, there's some that are larger, but it's quite manageable with what we need.
Definitely.
So yeah, so we're looking at this ideal case of a uniform pressure, uniform temperature, and we're just looking at what happens as this idealized sample of liquid evolves from methane rich to methane poor. This leads to questions. Well, how realistic are these conditions? Well, these require slightly cooler temperatures than have been seen on Titan. And we think it's reasonable that small-scale microclimate regional variations in temperature or due to evaporative cooling could push these liquids down into this stratifying regime. But that's up for debate. But what I think is really powerful is that this behavior is not restricted to these ephemeral ponds that form after rainstorms. This unique behavior of these mixtures will apply to all liquids on Titan, not just the shallow ones, but the deepest seas on Titan, which are 140 meters deep, if not more. But that leads to all sorts of complications with accounting for pressure gradients as you go deep into these lakes, for dealing with is there thermal gradients as you go into these lakes? How do these different processes change the behavior of these materials? And so what we want to do next is really explore what happens when we start looking at bigger bodies of liquid.
Yep.
And one of the first things we've seen that seems to be apparent is just what happens at the bottoms of these liquids. So nitrogen dissolves into these liquids at higher pressures, or we should say that more nitrogen can be dissolved at higher pressure.
Yeah.
So at the bottom of these lakes where there's a higher hydraulic pressure, one could expect more nitrogen to dissolve than at the surface. And then this would be a sort of a diffusion process as nitrogen has to make its way from the surface down to the lower layers. But in equilibrium, there should be a significant amount of nitrogen at the bottom of these lakes. Now, granted, these lakes are probably not static. There's going to be currents and things moving them around, but in principle, this behavior should happen.
Mm-hmm.
So we would expect that if these lakes are methane rich, that the bottoms of them could be very dense. But this leads to a very strange behavior of these liquids that we really don't experience on Earth in their viscosities. So on Earth, we're used to dealing with denser liquids, like honey or corn syrup. As they become denser, more sugar, they become more viscous. So honey is an incredibly viscous material, versus water. But on Titan, what we expect to see now is actually the opposite. As this nitrogen dissolves into these liquids, now we have to remember that liquid nitrogen forms at much cooler temperatures than either liquid methane or liquid ethane. So as we dissolve more nitrogen into these liquids, they become, in effect, more like liquid nitrogen. And what this means in their physical properties is that toward the bottom of these lakes, they can become denser, yet less viscous. They become thinner liquids. So they become denser, but more prone to flowing.
Mm-hmm.
And this could potentially lead to very strange dynamical behavior on Titan that we've just never really seen before on Earth.
Indeed. Huh. That's cool. Very cool. So you mentioned a few things about, where the community should go over the next couple of years. You even spilled some of maybe your next research projects, which is cool. So thank you very much. People, behave yourselves. But if you look in your crystal ball, right, where does community go over the next 5 years? Are there additional? You mentioned some of the experiments. Are there other experimental work that could be done? Is there new theoretical work could be done? Does one anticipate any new astronomical observations coming that could help clarify the situation in these lakes?
Yeah. So first off, to your initial comment, we love collaborating. So always feel free to reach out. But are there more observations coming? And the short answer is we can always defer to Dragonfly. Dragonfly will see something.
Okay.
Now, Dragonfly is not planning to go to the lake areas of Titan, so that might be a bit of a cop out. Potentially, if Dragonfly heads north, it might start encountering some of these lakes, which I think would be fantastic. We can start to see how these properties actually, how these materials and lakes actually behave. Beyond that, I think a lot of the observations that would be made would largely be atmospheric detections of materials in Titan, simply because it's just really hard to see down to the surface of Titan. It's a lot easier to see its atmosphere, at least at various depths into the atmosphere.
Sure.
So given that, I think one of the really great things that I would like to do, and that is to form a coupled Titan pool atmospheric model. And that's actually something we're in the process of doing right now with our collaborator Alejandro Soto. And so we're going to try and see how this behavior starts to affect the atmosphere. Mm-hmm. And of course, the long-term goal is always to form this coupled atmosphere lake geologic evolution model of Titan. That sort of the theory of everything on Titan would be kind of nice to that's always the ultimate goal here. But baby steps, one step at a time. We're working on the lakes. There's people working on understanding the properties, others that are working on understanding the climate, the weather patterns, the coupling between surface liquids and those weather patterns. And ultimately, it'd be nice to start incorporating dynamics of these lakes into those as well. But there's a lot of work we still need to do.
So we might know a lot before we actually get there.
It would be nice.
Very cool.
Well, Jason, where do you see this going?
So I think one of the really interesting places that I think we do have some data still to explore and look at are the effects that these liquids will have on the surface. And so we're looking, another group that's kind of working with these same data and working with us is looking at the ability of these liquids to do work on the surface and affect surface geomorphology. So one fun project we're working on right now is looking at the formations of deltas on Titan. And deltas, river deltas.
Deltas, okay. Okay.
So deposition of sediment at the mouths of rivers, and there are not many deltas on Titan. It's in one of the, it is one of the many confusing things on Titan. And so we've got a researcher, actually a 67P fellow, a PEG-B fellow,
Nice.
Sam Birch, is looking at modeling rivers on Titan and looking at deltas in particular. And we think that some of these unique fluid properties might be part of the explanation on that.
Okay.
So that's one aspect. Another interesting aspect is looking at lake dynamics. And we've got a grad student at Cornell, or at MIT, Rose Palermo, who's looking at shoreline processes and looking at waves in particular. But kind of a future aspect of that work is to look to see if these unique properties of these liquids might be influencing and affecting the way that lakes evolve. And so we can start to look at the surface expressions to see if there are hints and evidence of these unique properties of Titan's liquids on Titan's lakes. Another one that would be really interesting to look at is the effects of a lake's ability to do work on the base of the lake, based on the description Jordan was saying, where the lower layers of these liquids might be very, very thin. They, very low viscosity, very slippery liquids. So you could actually have, in essence, almost like a glacier type geologic process where you have a slip layer at the bottom. And so it might do different types of work than we might normally expect on a lake. And so lake bottoms may evolve, and sea floors may evolve differently on Titan than they do on the Earth.
Yep.
And another aspect, just to build on that, is Titan's orbit around Saturn has some eccentricity to it. And so you can couple potentially you could couple some of this with tidal forcing.
Yep. One
of the things I'm particularly interested in is to understand, can we get seiches in these lakes, or internal seiches? Seiches are these standing waves in lakes. On the Great Lakes around here, we can see seiches where it's just the lake sloshing back and forth.
Yeah.
And it causes water to pile up on one side before it sloshes back to the bathtub, and so the shoreline can recede, and then it comes flying back in. And can we have tidal forcing forming these seiches, or even a standing seiche or an internal seiche where the surface layer is flat, but if it's stratified, you have the top layer sloshing one way, the bottom layer sloshing in the opposite direction, and so you have this bottom layer sloshing back and forth on top of a relatively still surface. We're wondering what types of processes are going to happen on Titan, given that there's this very strange behavior of material properties. There's different tidal forcing on Titan than on the Earth, and just this fundamentally different behavior. I think this work just goes to show that we think we answer one question or understand one, and it just opens up so many more doors.
Yeah, awesome. Yeah, a lot of great work still to do on Titan. I look forward to seeing some of your future articles on this topic. It'll be great. Jordan, Jason, I want to thank you very much for spending some time and walking us through your PSJ article.
Thank you. This was a pleasure.
Thank you so much for the time.
All right, everyone. Thank you, and we'll see you on the next one. Bye-bye.